want to a little bit more formalize this one. We will look into generating methods and instances, introducing class variables. We will look into what else do we do? We're doing class method. We will do static method, and we will do some inheritance. So that's a little bit the topic for today. But before we starting off, I found a really nice YouTube video which I want to show you. So just that it's not getting too dry. Let me know if you can't hear the sound, but I'm just putting it here, and I thought it's very interesting and has got a little bit to do with our topic today. So let me just start this one off.
I need to find the best way to learn math and science.
So let's
it's brilliant.org.
Whoa.
There you go.
"24 hours later." Later.
All right, that was a little bit of a fun video for introduction. So don't do that. And for this one, we wouldn't need any packages. So don't worry about any packages. I just thought that we have got later on, I think, if you're looking down here in our course, I will do also a course in time series data 1 and time series data 2. So we will talk a little bit about programming in Python and using or applying it to time series data. So let's start off. So I will do everything. Let me just, if someone is interested in the video, I think it's pretty quick. I can put it in the chat. So just some entertainment value in there. So I'm doing everything. I will program everything in an empty Colab sheet, and I encourage you to type along. We will do some exercise in between. As usual, I'm going to share all my code at the end of the class. So if you can't type along, you will get all the code at the end of the class. But hopefully, I'm a very slow typer, so it should not be too difficult. So let's start off with just in general. So I'm not expecting you to have got any knowledge in object-oriented programming. I do expect that you have got some kind of background in Python. So we can start off very easily of just declaring a variable called x equals 1. And we want to know what type of these variable x is. So we can say print, and we say type of x, right? So we're running this one. It will take a little time because I'm just starting off my runtime now. So now the class is called int for integer. Let's do a different one. Let's do def hello. And print hello. So we know that this is going to be a function. To test this one, you can also say print type hello. And it tells me my class, the class of my, it's called also object, is called function. Let's do another one. Let's do y equals hello. And we're doing print type again of y. And it is a string. So now we explored already classes which are predefined in Python. So that's a predefined class in Python. If you want now to do some kind of, it's called methods. So we want to apply a certain operation to our variables. So let's say that we have got, what could we do? Is we can say that we have got x declared, we have got y explained, so we can say print. So we say the print method x plus y. All right, so now what we're getting is we're getting an error message, and it basically says that, you know, you can't add a string and an integer together. So that's not defined. This kind of method is not defined. It will only work when you have got two variables which are declared as the same type. What you can do is you can say, for example, you can say that there is a method. So if we say print and we say string dot upper, so that's a method which is defined for 4 characters. And we need to declare our string. Hold on. Let's say we just declare the string. String should be, let's say hello again. And so the string is a character, or a string. No, the string is a string. Sorry about that. And then it has got a method called upper. So what it does is it will convert our string into upper cases. So this is called a method. So now we know a little bit about objects and methods. So now we just plotting along and we starting our first own class. So we create a class. Let's do, I just put a little bit also a few comments in there, so it's easier for you to read. If you're downloading it, we say a class, and the class we called employee, single name, employee. And all we're doing is we're just generating the class. So we have to say pass. Pass means it just passes everything, but there's nothing really much onto it. So it's an empty class, and it's just defined as employee. So if we just creating an instance, so we create instances. In this case, we're doing 2 of them. We say our first employee, number 1, equals employee. There you go. And then we're generating a second one. Employee. All right, so now we want to see, let's run this one quickly. That should run. And then we say print employee 1. And it tells me employee 1 has got a class, and the class is called employee. We can do the same for the second one. We run the second one, same thing again. So what we generated is just a class with no method, with no properties, nothing. So what we can do is we can use the class as the following. We can say employee one, and then we can add first and say the first name should be John. Say employee one, and we can say that he has got last name. Last name equals, what do you give it, Smith? We can give employee number one. We can give him an email. And then that should be, let's say, john.smith@company.com. So we give him an email. And we say employee one.pay. So this is his annual salary. In this case, we can say, let's say 80,000. All right. So that's our first employee. So employee is class of employee. And we can also do a second one just to make it a little bit more interesting. So we copy all of this down here. We do a second, generating a second one. And we say that's Sarah. Surname is Johnson. And its email should be and she makes, let's say, 90,000. All right. So we run that. And now what we could do is just to check that everything is in there, we can print. So we can print some of the properties we just defined. So we can say employee number one, and we want to know what the email is. Here you go, email. We run that. So here you can get the email. So we can call it by employee number one dot email. We can of course do the same thing with the second one, number two. And we have got both of the emails. Hold on, employees, sorry, Johnson. We need to put it in another line. Hold on, let me just check. Johnson. Let's see if I've got anyone sees any, probably did a typo error somewhere. Number one, number two, Johnson. Anyone can help me on this one? I do have got my cheat sheet, so I can always go back to my cheat sheet to see if I made any typo errors on that one. Let me just double check. Anyone sees the error?
I'm getting the same.
Say that again.
I said I'm getting the same result.
Well, let me just double check. So we have to go there. So what we want to do is we defined everything here, employee. Let's just go back to that one. So we have to see employee. This one is all good. Let's just run this one again. We print employee. There we go. And then we run quickly this one in one line. And here we go. So what was the difference there? Employee email. Did you see where? because I just used my cheat sheet. So let's go quickly through this one to see if someone has got still the code with them to let me know where the mistake was. As I said, I'm going to give you the file later on, so it should all be good. Anyone could see that where my typo error was? Otherwise, we just continue from there.
On when we declared employee 1 to employee, we didn't put the brackets at first.
Okay. The instances, right?
Yeah.
Where we declared the instances. Okay, so I forgot the brackets over there. So if you're changing this one here, then you should get the same result. All right, so so now what we could do is we can check. So we can say dear for employee, and we can see that what is defined within our class, and we can see all of these predefined methods. So that's all predefined methods. They're all starting with 2 underscores, or dunders it's called. So there's nothing from us defined now as a method. And what we like to do is we would need to do all of this one for each employee we're doing. So we have to assign each individual employee to first, last, email, pay, and so on and so on. So to avoid this and to explore a little bit the class, we just go in class, employee. And now what we're gonna do is we define, and then we do in 2 underscores, the initialization. So it should come up as init. And it says self. So that's usually you're always initializing it by itself. And then you want to initialize your first name, your last name, and your pay. So that's with the email here, we can actually probably put this one together. So all we need is we need to initialize when we just basically assigning our instances to the class. We're saying that, okay, it needs to initialize itself. It needs to initialize the first name, the last time, and the pay. So we don't do none. We'll take this one out. And we have got the pass down there. So pass, we don't, because now we're actually passing certain things. So we do self dot first. There you go. So that's what has been initialized, and we're using this one, and we're calling it exactly the same name called first. Same for last, self dot last. So that's the initialization, and we call it last. So we can, use the same names within our class. We say self dot pay, and we say pay. There you go. And we say self dot email. And I think we can generate the email by ourselves. So let's say that first plus, and then we're putting a dot in there in between, plus last, plus, and then at company.com. So what our class does, it requires that you define your first name, the last name, and the pay, and it would generate basically the email by these defaults. So everything will be at company.com. All right, so this is our class now. So we did some initialization. We initialized all of the required properties, and then we assigned the email. So let's generate the employees again. So we instance, here we go. Employee number 1 equals. So now here we had got employee number 1 was first name, last name, email. Now, since we declared already that there is a class and it requires to have got a first name, last name, and pay, we can basically say that our employee one is instances, or is an instance of employee. Here we go. And then we can say that, okay, so our first name is John. The second name is Smith. And his yearly income was 80,000. 1, 2, 3. We're doing the same for number 2. And she's also employee. Here we go. And we had got Sarah. And her surname was Johnson. And 90,000. All right, so we run that. And now we can check. So you can see here, we declared all of this one for each individual employee. And we assigned 2 instances to employee. So basically exactly what we have done up here. We had got empty class. And then we had to do all of these assignments here, all of these ones here. So let's see if we're getting the same result. We can say print employee one dot email and print employee two dot email. P the same. There you go. Underscore. Here you go. So it's exactly the same. It generates exactly the same. And now you can see that if you have got a lot of employees in that company, you can basically just generating these instances by just typing this one. So you don't really have to do, all of this one here just by basically generating each property of that instance individually. So now we want to generate methods. So we're starting off with generating just a general method. So let's try to do print. And what we want to do is, this is just formatting, is we've got the braces, space, braces. You will see that it's just formatting, dot format. And in this case, we want to say employee one dot first name. There you go, first, comma, employee one dot last. All right. So what it does is it just basically prints out where the braces are. It just includes our employee first name and employee second name. So that's kind of like a function we're running, this print function, and we can use this one to include this one in our class. So what we're going to do is we can use our top one here. So we just keep generating that, putting it down here. So exactly the same. So I will always use the same code. So just getting stuck is I'm just copy pasting the same code. And in this case, we have got our instances down there. We keep them. And now we generating a method. There you go. So generating a method, same as above. We can say that defining, and then we can call it full name. Full name. All we want to pass over is self. So we just using self for this one, and we say basically return. And we returning the same as above here. So let me just type this one is the the brackets again. Return the brackets. Dot format self dot first. There you go. Comma self dot last. All right, let's run this one. Let's see if that works. And now we can say print employee one dot full. So now we have got full name. And since it is a method, we have to use the brackets there as well. So John Smith. So what we did is we used this kind of print function to define it as a method. And then now we can do the same thing for applying that method to employee 2. There you go. And we have got Sarah Johnson. So we have got these method, which just basically prints out the full name, puts together the first name and the last name and puts a space in there. All right. So what we're going to do next, we want to do, so we can introduce, so far so good, everyone could follow? All right. So now we do something called introducing class variables. So each class also can have got variables. So let's grab the code here up here again. Copying it down. The second bracket after the return. So this is just formatting here. I just got a question of this piece is just basically saying that, you know, it needs to return in that specific format, the first name and the last name. So that's just a formatting syntax. So we can introduce a variable in our class. So we still have got exactly the same what we had before. And we can say that, you know, every employee, let's say, get the raise in their salary. And we call this one raise amount of, let's say 4%. So they're getting a raise every time at 4%. So what we need to do now is we need to generate a method where we actually increase their salary. So if we generating the instance, we then have to generate a method to increase the yearly salary by 4%. And now we just say def, and then we call it apply dot raise. And all it needs is self. And then we can say that self dot pay. So we want to increase the pay equals an integer. So we just want to keep it as integer. Self dot pay times self dot raise amount. That's all we need to do. All right, so let's go through this one again. Is underscore. Hold on, I can't put a dot in there. I need to do an underscore. That won't work. So introducing the class variable. So we have got our raise amount is 1.04, so it's 4%. And then we have got a method which raises, let's take this one out first, raises that by the amount we defined in the past. So let's run this one, that ran through. And now we can assign our instances, generating our instances, same as before. Just get some more. Same as before. And now we can say that print. We take employee number 1 dot raise amount, and it tells me it's like these raise amount for employee number 1 is 4%. So let's apply that. So all we need at the moment is we just queried. It's our instances employee 1 is of the class of employee, and the raise amount for each individual one is 4%. So let's say print employee 1.pay, and we can say that employee number 1 dot apply raise. It's a method, so we need the 2 brackets, and then we print out the employee's new pay. So let's see if that works. All right. So first, what we did is we printed the employee's pay, which was 80,000. That's what we defined up here, and then we applied the raise. So here we went back to the apply raise, and it multiplies our pay with the raised amount, and then we printed that one out. And of course, if you're doing the same for number 2, employee number 2, who has got a little bit of higher pay, we run this one as well. You can see that she started with 90,000 and she got 4% of increase. I think one thing you can check is you can say print, and this is just in, let's say, employee number 1, and you can say dictionary. It's also, that's one of the, remember at the beginning, we had got all of these predefined methods, and one is called dictionary, and we run this one. And here you can see that it actually prints you out what the properties of each individual instance is. So the first name is John, the last name is Smith. Pay is such and such, so that has been increased now. And the email is that. Same thing, gonna apply to employee 2. So this is just for you to check if you have got a certain instance, you're just putting it in there, you're putting the default method dictionary in there, and then it gives you the output. So that's how you can double check. So now let's do the following. Let's do employee 1 dot raise amount equals, and then we overriding that. So at the beginning, what we said here, up here, we said the raise amount is 4%. So now we decided this one should have got actually 5%. So we just only increasing the raise amount for one single instances from 4% to 5%. Let's do print employee number 1 dot raise amount. And then just to double check, we can say print employee 2, just as a comparison, dot raise amount. So what we're doing is initially we said that everyone has got the same raise amount, but now we're overriding the one for just the first employee. And here we can see that we raised the amount only for the first instances. So only for employee 1, we raised the amount from 4% to 5%. And of course, for the second one, we didn't change anything, so it remains at 4%. And then here we can just double check. And here is like just for practice, you can say print employee. Oh, we've done it already up here, right? Doing it here. And yeah, we've done it already up there. So this was class variables. Let's see what we can do is we have got another class variable example. Let's do another class variable example. We just take in all of this one again. Getting our employee object has no attribute raise amount. Let's see. It's just putting this one back here. So you should have got this one, and you have to declare here raise amount up here. That might be the one you're missing. So raise amount you have to define. So we're talking about our class variables, and in this case we defined our class variable as raise amount as 4%. So you do have to declare this one at the very beginning. Otherwise, it doesn't recognize that. I hope
I
that
do have it
works.
defined at the very beginning. I'm still getting that error.
So if you do print employee _1 dot, and then here it should already come up as raise amount.
Yep, that worked. Thank you.
So yeah, you should. And what we do now is we're just introducing another one. So what we want to do is we want to every time you adding an instance. So in this case, we had got two. We had got employer 1 and employer 2. We want to count the employees of the company. So that's what we're going to do. Is for this one, it's always a good thing to say number of employees equals, and then first of all we say 0. So we're starting off that number of employees is 0, and then we have got where am I? This one is we can use this one as in the initialization method. So every time an instance gets initialized, this is what we run. So every time you're just defining an instance, it will get a first name, a last name, a pay, and it will generate the email. What we want to do now is we say every time it's being initialized, we want employee dot, and then we set number of employees plus equals 1. So the counter of employees every time you're initializing this one should run from 1 to 2, 2 to 3, and so on and so on. So increment. Let's run this one. Shouldn't be any error in that. Putting some more down here. And now we could do is print. So first we want to print employee dot number of employees. So if you run this one, the number is 0. So we just initialized the whole class. We just set everything up. We haven't created any instances. So it is 0. So now we just, as we are a little bit on the lazy side, we just take in our instances from up here, putting them down here. And now what we're going to do is we just do exactly the same thing. So we just copy this one down here, and we run that. So we print first, should still be 0. And then we initializing employee number 1 and employee number 2. And then, of course, the number of employees then increased from 0 to 2. Right. So now let's have got a look. So we looked up here. Remember, we looked up here. We had got our class which had got nothing in there. It didn't had got any initialization. It didn't had got any methods. So this is how it looked like. We only had got all of these default methods. So let's see how it looks now since we added, all of these code here. Just going down here, putting this in here, and now we can see that it has got also all of these standard ones, which is starting with the 2 underscores, and I think this is usually called dunder. So dunder are the default methods, which are coming up every time you're creating a class, and you can actually change them. But I think that goes a little bit beyond of the class I want to go through today. But then at the very end, you can see that, okay, we have got a method called apply raise. We have got a method called full name. We have got actually a variable called number of employees, and we have got the raise amount as a variable. So it shows you the variables as well as all the methods. So let's just do, I think I have got, before we go into the next ones, I have got one example where we're doing the stock example. So I'm just doing a little bit to practice. Let's put in here some text, just making it a little bit separate, and we're doing a little exercise as a stock example, because we do have got enough time today. So we say class, generating new class called stock. And what we're going to do here is define course in initialization. So we need to initialize that. We need to initialize. Here we have got self. So we always start with self, and then we want to have got a ticker. We want to have got an open price. We want to have got a close price, and we want to have got a volume. So later on, you can download all of this from Yahoo Finance. I will demonstrate, I think, this one in the time series analysis, but for the time being, we don't really want to bother too much about packages on this class. So we won't use like any imports from Yahoo. We're just generating our instances by ourselves. So we have got volume. None we don't need. And then say self dot ticker. And we call this ticker. We do self dot open. It's our open price equals open. We need self dot close as close, and self dot volume equals volume. All right, so we're passing something, so we can take this one out. And what we also want to do is we want to generate the return. So we can easily generate the return. So if you can say self dot rate underscore return. So it's similar to what we did up here with our company. So we're generating a new property in this one, and this will be, let's say it's float. We give it a type float, and then it's close divided by open minus 1. So that's our return. What else do we want to do? We need to have got a method called update. So now we need to update our ticker. So we say define update self open and close. And all we're doing is we say self dot open equals open, self dot close equals close and self dot rate return. Self dot rate return equals our float self dot close divided by self dot open -1. So this is when we're updating this. So initially that gets all initialized with that one. If we want to update our returns, we have to apply that method. And then we want to define a print method. So we want to say print return. And all we need is self. And we say print. Need to get the print self dot rate return. It's all we need. Let's see if that works. So just quickly going through this one, we initialize everything. We just initialize the ticker, the open, the close, the volume we might not even need. We're defining the rate of return. Then we do an update. So if you want to update the returns, we have to initialize the open, the close, and regenerating the return. And then we just have got the print function. So let's put 2 instances in there. We're just calling it Apple stock. And this one, it's stock. So it is a class of stock. And the ticker is usually a AAPL, right? Let's say that I just make up some random numbers. 69, that's our opening. And our closing is 144 point, probably different now. And our volume is, let's say, doesn't really matter. I don't think we need the volume as itself. So you can just do some random numbers. We can generate Google. It's our second instance stock. And it is Google, and just give it another. I draw down some numbers. I don't know if they're correct or not, but this is basically what you then would import if you're doing a query in Yahoo. Just basically pulling in your opening price, your closing price, and the volume. In this case, 1561616. Let's try that one, and we're generating that. All right. So now we can just double check is, let's say, Apple dot ticker. And here we go. So we can see that it has been generated. So instances has been generated. And we can say Google dot print return. So we're just printing the return. This is the method. So this is, we need the 2 brackets in there. And let's see, Google, okay. Little typo there. Print return. Print return. Let's see. Google print return self. Stock object has no attribute print return. Let's try this one again. It should come up automatically, right? Did this one right? Let's see. All right, let's see if there's any mistake in there. It's return by itself, print. Is it? Sometimes they're very sensitive about the, let's see, that was the problem. Run this one, we run this one, and we run. Print return, here we go.
I think you need to add the brackets.
On print return, that could be. Very good point, because with the method, there's no attribute. Let's try again. Google. Let's do open. So that should be working. All right, that works. And we can say Google dot let's see.
Could it be the indentation of the definition for update and print return?
That's what I thought as well. That's what I thought as well. So let's see. That's a very good point. Let's see if this, because it's very sensitive. Let's see if that works. That works, and then we need the brackets, and off you go. Thanks very much. Thank you. That was a problem. So you have to be a little bit cautious about, I didn't see that one, is all of our definitions for the initialization and for the other method we predefined, they all need to be aligned. So that's a little bit the bad part in Python, that you have to pay attention to the indentation. So we have got print return. And then what we can do as well is, since we did the update, so we have got here the update, so we can check the method update. So we say that Google dot update. There we go. And then we want to update the opening price. So the opening price is some number. And a closing 0.4. And then we can Google dot print return. We can run this one. And now we can see that it has been updated. So this is our second method we introduced, is basically the update. So we said that we want to update our pricing, and we only needed, in this case, the opening and the closing price. And then we just put the print return in there. So that was another example. All right. So we talked about methods, and let's see where we are. We have got methods, and that's called the general method here. These ones here. And we're going to steal the code from up here again. So we want to continue with our employee class. So we copy this one down here. And what we like to do now is we want to introduce a different method. And this is called the class method. So what you're doing is you basically, after, I think, apply here, we can do the following. We can say that add class method, and it comes up. So this is defining a class method, and what is called the decorator. So this is called decorator, and the decorator basically says that, okay, I want to have got something else than just the standard method I'm introducing there, and has got certain formats. So this is all being defined in Python already. So what it does is, so first, usually what we did is for our methods is we have to call it itself. So that's for the normal method. For this one, we're actually using the class. So our first initialization would be like define. So we can say the same thing, define set raise. So we set raise and amount, set raise amount. And now what we did in the past is if you have got the standard method, there's the first one would be self. But what we want to do is we don't really want to do all of this one here, self, first, last, and so on and so on. We only want to take everything and we want to basically take it from the class itself. So in this case, our first argument would be class. So we can't use the word class, or it's usually defined as CLS. So that basically means that it takes the class itself. So in basically it uses all of the defined one in class, and then of course we have to put it as an amount. So that's what we're using in there as well. And that's going to be very short is CLS. So as our class of raise amount. So that's what it's defined already there, equals amount. So this is the difference, is we're using a different method, and the difference between the general method and the ones we're generating as class method is it uses the class what's already defined. So we don't need to have got all of this one here, first, last, and then pay, and so on and so on. We're just taking this one. Let's quickly run that so we know that it runs well. And we're just generating our two instances. So we're stealing our two instances again. Our first employee and the second one. Here we go. We've got our two employees. We can say print. And in this case, we say employee dot raise amount. So this will be raise amount. In general, we put at 1.04. And we can do employee dot set raise amount 1.05. So what we try to do, and maybe that wasn't that clear, is with this method, we're basically increasing the raise amount for all of the instances. So for employee 1 and employee 2, it should be increased by all of them, because what we did up here when we said that, where was it? Here we had got this method, or this, this part actually only raised it for employee 1. But now we generated another method which raises the amount of increase of salary for all of them. So in this case, we're going to set this one to 1.5. And now we have to print it out, of course. We can say that print employee raise amount, employee dot. We do this one, yeah. Employee dot raise amount. Can put everything below each other. Print employee underscore 1, just to double check raise amount. Here we go, and we're doing the same for print employee 2. Since we have got two employees, dot raise amount. Dot, there's a P missing. There you go. And we run that. And now we can see that we applied raise amount 1.5. It is being applied to all of the employees. That's what this one means. So we have got 1.05, so 5%, and it also increased the amount by 1% for each of them. So let's do, so we have got class method. Let's do one more example on class methods. As usual, we steal our code here. Putting it down here. And we have got the following. We do the following. We have got the following problem. Let me just type this one down here first. Is we have got employee underscore string 1 equals, and then we just basically say John Doe 70,000. 1, 2, 3. We have got a second one, employee SDR. That's just a variable for the second one, equals Steve Smith. He works part-time, so he only gets 30,000. And we have got the last one. Equals Jane Doe. And she makes the most. She makes 30,000. So this is our problem, is we don't really, sometimes we don't really get these nice first name, last name. Everything comes in a string format. And what we want to do is we want to introduce a class method to actually define this one in the first name, in the last name, and in the pay. So how are we going to do this? So we're just using the class method again. Class method, here we go. We define from string. So we see down there, we see the string, and we want to nicely have a first name and last name and the pay. From string, and what we need is, as the class method describes, our first one will be class. So that's our class we need, and we need our employee string. These are the ones we defined down there. So this is what we need to do. And let's say first, comma last, comma pay. So this is our 3 properties of our instance, equals employee underscore string. So that's what we're reading in there. Dot split. And we got to split it by the minus sign. This is how we're going to split that. Of course, we need to return something. So we're returning, in this case, class of first, last, and pay. That's all we need to do. So for our class method, we just loading up the string. Here's the string. Of course, we're getting all of these first name, last name, and pay. We already taken over from the class, so we don't need to define that. We say first, last, pay. So we have this one already within our class. We say that it's going to be, the string should be split by the minuses. So the first one will be, the first part, John, for example, will be assigned to first, Doe will be assigned to last, and pay will be assigned to 70,000 in this case. And then what it does is returns to our class the first, the last, and the pay. Let's run that one. And then we run again this one. And then we want to say what we can do is can say new employee. Let's see, that's yep, new employee underscore 1 equals employees dot from. So we calling from string. That's our method, and we pulling in our, let's say the first one, employee string number 1, and we want to print new employee, and we want to know the email. Let's print the email, and print new employee, and we want to get the pay. See if that works. Here we go. So we have got these defined, and we can change this one as we want. So if you can say that, you know, we can run it through all of them. Let's just do it for 2. We do the same for 2, and we can see, okay, there's a problem there. So new string, and print, got this one, missed one. All right. Here we go. So that's the same thing. Is what we did was we had got the string, we applied the class method, so we converted that string into our properties, first name, last name, and pay, and then we applied email to this one. So we basically ran from the class method, which we first run, and then we went back to our initialization, and that generated our company, and we generated the pay as well. So this is called, what was it? This is called class method. Class method. There's one more method I want to show, and this is called static method. So let's put in here text. I should have done this one above as well. That a little bit. Go. So static method. So we've got the normal method, we have got the class method, and we've got the static method. The static method is basically, it doesn't need anything. It doesn't need to be, let's steal this one again, so we know that everything is running. There you go. It doesn't really uses any of the properties from our class. So in this class, let's say that we want to do a static method. So we need our, it's called static method. And so it doesn't need to depend on the instances or class. The first argument is going to be nothing to do with the class. So what we want to do is we want to see if we have got, we're generating a method which tests if our day is a work day or a weekend. So usually it's being counted from 1 to 1, 2, 3, 4, 5, 6, where 5 is a Saturday and 6 is a Sunday. So we say define. So we're using the static method. Define is workday. And since we don't really use anything, we don't need to use anything of the employees' properties, or we can say day. That's it. We don't need anything else. So we say if day dot weekend is equals 5, or day dot weekday, weekday or day dot weekday is equals 6, then return false. Otherwise, return true. So this is our static method. True. Sorry about that. Here we go. True. Let's run that one. And what we can do is, let's see, we have got everything we need. We can do the following. We can say that import. So we do need to have got one package in there, import datetime. And we say my underscore date equals date time, which we included dot date. So we're just generating a date. We say 2016, 7, 11. And I think that should be a Monday. I looked it up, I think. And we say print. And we still in our class employee can say is workday. And of course, we need to put in there my date. So this one is true. So this one, I think, is a Monday. So if we putting in here, say day before that, let's see if that works, is false. So that's a Sunday. So we can run this one. So just as a summarizing of all of the methods, before we go to inheritance, is we've got 3 different kind of methods. We have got the general method, which is these 2 up here. We have got the class method, which are the 2 up here. And then we have got the static method, which is down here. General method, you have to declare everything. Class method, you basically take in all of the properties from the class and using them. And for static method, you don't really have to do anything. So like you can see here, we didn't use any of the properties from employee, which we defined earlier. We're just using the weekday and we're putting it into our class. All right. So this is methods. So the last thing we're talking about is inheritance. So the cool thing is, let's put it in here. Inheritance. One of the big advantages to use object-oriented programming is that you can define a class and then you can declare subclass. So in this case, let's go back here. We need everything. I just have got a little bit of, let's use, I don't know where this one comes from. We use, what we need is, we need full name, we need race, and that's basically it. So we just take the top part here. We won't use the class method or the static method. So we're just going back to this one here. We just defined, I think we don't need the race amount. The race amount we might need. We don't need this one. I'm just cleaning it a little bit up. So, and I think we don't need this one. Just to make it a little bit easier to read. So this one still runs. This is the same as we had got above. We just got rid of some of the method we introduced. And what we can do as well is we can now do another class. So let's say initiating subclass. So in this case, we can say class. And then in our company, we can say that, okay, we want to have got a class called developer. So it will be a subclass of the employees because the developer will be, sorry, the developer will be also be an employee. So we can say developer. And every single developer will have got the same properties as our employees. So every developer will have got a first name, a last name, a pay, and an email. So the easy one to do here is we're just putting in here employee. So that makes it a subclass of employee. All right, so let's say that developers getting a higher raise than ordinary employees. So we can say that raise amount could be 10% instead of only 4, which you defined up there. So we say that, okay, the raise for developers is higher than the normal employees. And what we can also do is we can define another initialization in it. Hold on. And in this case, we say self. We have got a first name. We've got a last name. We've got a pay. And we're also adding a programming language. So we have got developers, and the developers, they can have got different programming languages. So for example, they've got Python developers or Java developers. So in this case, we say programming language. So normal employees, which are not developers, they don't have this, but for developers, we have that. So now we can basically do the following. We can say super, hold on, let's just do, I just have to be careful with our thing. If I do the, okay, goes in here. This is super dot init. There you go. First, last, and pay. So what it does is in this class, we just basically saying that, okay, we know that this is a subclass from employees, and we let the class employees handles first name, last name, and pay. This is what's been taken over from the class employee. So we don't really have to do what we did here. We basically using that part here. We don't have to define this one anymore because we know that it's a subclass of employee. So then we don't have to do this one, all of this one here. The only thing now we have to take care of is, of course, self.programming language equals programming language. That's all we need to do is all of this one here, all of these ones here, this is going to be replaced by that one here. And all we need to add in addition is our programming language. So we run that. And then, of course, we expect something. So I think we have got double bullets here. I hope that I did the indents all correctly. Let's see if that works. We will find out. So that runs. So now we have to generate our instances. So now we have got developer number 1 equals developer John Smith. And let's say 50,000, 1, 2, 3. And he's programming in Python. And then we do developer 2. Developer, the name is test. I'm just running out of names. And he makes 60,000 and programs in Java. There we go. All right. So now we can say print developer 1. Here you go. Dot raise amount. Raise raise amount. Is that correct? Print developer 1 dot email and print developer 1 program language. Here you go. The first one, I think raise amount is wrong. Let's do raise amount. Here we go. And here we go. So here what we did is we generated a developer, which is part of the subclass developer, which is a child of employees. And we set the raise amount instead of the normal employees, he getting a raise of 10%. We generated the email. So this is from the normal class. We didn't have to do anything in developer. And we have got the additional property called programming language, and this is Python. So I think that's what I want to demonstrate on inheritance. Of course, you can, there's different, you can increase these kind of classes. You can generate a manager and these kind of things. So that's how you can build up. So you're basically taking the methods as well as the properties from the class employee, and then you just generating the subclass. In this case, it was developer. And we introduced another field called programming language, and we did generate a new class variable, which is here the raise amount, which is 10%. So I think now I'm a little bit running out of time, so I can stop here. What I promise you to do is I will save this one down, download. I download it as a Python, as a Jupyter file, and I'm going to save it down as a normal Python file. Here you go. And then I will have got a look in my downloads, and I will put these ones in the chat. Let me see if I can do it side by side so it's easier. And then you should have got everything. Can I do this? Let's see. Let's do one by one. That's number 1. And this is number 2. All right, so I hope you learned a little bit about object-oriented programming. It was just an introduction, so for everyone who's already programming in object-oriented, that's probably was just a little bit recap. There will be other classes coming up, so let's see. Have got a look at the other classes. That was me today. There will be, oh, that's me again. Okay, so we're doing time series data 1, data 2, and this is in a week's time. So that's next week. We will talk about generating time series. It doesn't use that much of object-oriented programming, but it will use a lot on packages, and especially packages being used for object or for time series analysis. This is 2 parts of it. So if you're interested in that, I hope I can make a little bit of practical examples on this one. I know that today was a little bit very dry, but since I gave you the video at the beginning, I hope that cheered you up a little bit. And I hope I'm going to see you next week on time series data. And thank you very much for joining me today. And I hope to see you again.
Thank you.
Thank you, Professor.
Thank you. Hey, Ben. You still there, Ben?
written books, math books, who after writing the book swore they'd never write another book because even a couple of years after publication, they're still finding typos. So it's a very frustrating thing, but typos exist. All right, so if you have any questions, raise your hand. It's probably better to speak up directly because I'm not necessarily looking at the little chat bubble. So sometimes I miss seeing it when someone asks a question by chat. So just go off. If you do have a question, just go off mute and ask the question. Just interrupt directly. It's the easiest thing to do. And secondly, before we start, we are going to take two little breaks, working breaks in between, and that provides it's a 3 hour session. So there's a good chance that at some point you'll want to get up for a minute or two. And so I've tried to put that right into the presentation. All right, so let's begin. So much of what we're going to do today refers back to the original arbitrage-free models of interest rates found in HJM. That's a paper that's now 31 years old. So it's not the it's not exactly brand new stuff, and there have been some enhancements of it, making it more relevant to markets as they exist, markets as they trade. And so I've tried to include some of that at the end. But the fundamental idea behind Heath, Jarrow, and Morton is something that still it's still canonical in the industry. The idea of arbitrage-free pricing and building a term structure of interest rates based on that. Now, if you do try to, I've got a link for the article in there, and if you do try to read the article, it's very mathy, very hard to read. And so we're going to go walk through the steps. We're actually going to turn a lot of what's in the article, which is very dense with stochastic differential equations. We're going to turn a lot of it into arithmetic. And we're going to, and the trick to taking something as complicated as the Heath-Jarrow-Morton model and turning it into what basically amounts to an arithmetic problem is that it gets very detailed, and you have to keep track of every little thing that you're doing. So it becomes part arithmetic, part accounting, double entry bookkeeping almost. So it's very, very technical discussion. Some of it you may find a little dry because we're going to try to be precise all the way through. But by the end, what you should have is a firm grasp on rates, on yield curves, a practical understanding about how yield curves evolve, what the factor structures of yield curve evolutions mean, how they ultimately you'd want to think about if you're evolving a yield curve through time to price some derivatives, some sort of instruments that have a payoff based on a future rate. You want to think about how the yield curve evolves, and you want to get it in your mind, a picture of how the yield curve evolves, how even if it starts as a downward sloping yield curve, if there's a multi-factor representation as you evolve through time, what you'll find later are the adjustment terms tend to accumulate, and that accumulation of adjustment terms in a multi-factor model means that even if you start with a downward sloping yield curve, project out far enough and it's an upward sloping yield curve. So some of this is very nuanced. It's a lot of fun though, once you start playing with it. it's more fun to play with than to try to explain to people. But hopefully after explaining it to you, you'll get to play with it and have some fun. All right, so first, a lot of the what we're going to do um, is based on the idea of recognizing that it's a very trivial thing to say, is that a bond price is convex. And so it's not a linear function of interest rates, but it creates this sort of concave picture. And so if we think about an expected forward price versus the forward price at the expected forward rate, those are two different things. And what we're interested in are expected forward prices, and forward prices and expected forward rates. So we want to keep that distinction separate, and that's going to lead to one of the terms that accumulates. We'll call it the adjustment term. In the notation that evolves, it's got the label alpha. That's the label that HJM gave it umpteen years ago. So we're gonna look at that differential between the price, the expected forward price, and the price at the expected forward, or the forward at the expected forward price. And to put some numbers on it, if we think about discounting an instrument where rates next period might either be 8 or 12%, and we're not sure which, I suppose there's 50-50 odds of each. We could value the instrument at a price of 8%. We could value the instrument with a discount rate of 12%. We can find the price at the expected forward rate, which is 10%, or we can find the price based on the combination of the low and the high rate. And you'll see that necessary adjustment term is the difference between the forward at the expectation versus the expectation of the forward. All right, so let's talk a little bit about term structure of interest rate theories. There's been a fairly long evolution of interest rate theories, some of which date back to well, this is how old I am. I never had John Culbertson, but I used to see him walking around the halls a lot. The market segmentation theory, which was that there are different market segments that are attracted to different maturities of bonds, of securities, especially treasury securities. So, for example, insurance companies are interested in long-dated securities that they could use for capital. They're not interested in the repo market per se, or the very shorter end of the yield curve. They're only interested in the long end. So one theory is the segmentation theory, that there are clusters that have different attractions for different maturities, and that's what gives rise to the shape of the yield curve. There's another theory sort of attempting to explain why the yield curve is generally upward sloping, and that's attributed to Keynes with his liquidity preference theory, and that premiums are required for longer maturities because the longer maturity bonds are typically more illiquid. There's a preferred habitat theory, which is very similar to market segmentation theory. attributed to Modigliani and such. The two that are of interest to us. So that's 3 for a history lesson. The two that are of interest to us are the expectations hypothesis and the local expectations hypothesis. And for us, it's the local expectations hypothesis. They're both very similar, but it's the local expectations hypothesis that instantaneous expectations are indifferent to maturities, or are indifferent to maturity. A blip in spot rates affects all maturities, although it may affect them differently, but it affects all maturities. So let's start looking at the local expectations hypothesis, and then we can start playing with things. All right, so suppose we had prices of 1, 2, and 3, 4 period bonds. And this is the kind of notation that I'll be using without. So the 1 period bond is pricing it as of today, is the price at time 0 to time 1. Price of a 2 period bond is, and these are bullet bonds, 0 coupon bonds. The price of a 2 period bond beginning today would be P02. P03 is the 3-year 0, or the 3 period 0 beginning today, and P04 is today's price of a 4 period bond. And this really is what drives everything. We assume that the no arbitrage relationship, and I'll explain this form in a second, under the local expectations hypothesis holds. So, and that is that the price of a bond from today, 0 to K, is the same as the price from 0 to T to delta T, and then a forward starting bond or a future that begins at delta, so pricing it today, but it runs as a bond from delta T to K. So the price from 0 to K can be decomposed into 2 components. So we may observe a price of, say, a 2 period bond, so a bond that goes from 0 to 2, and we may observe the price of a 1 period bond that goes from 0 to 1, and then the future on a bond 1 period out, that's a 1 period bond that goes from period 1 to 2. And so this relationship implies that the following forward prices exist at time 0 if we're going out 4 periods. And one thing to note is that the instantaneous forward is the same as the is the short point on the yield curve. So the forward prices of bonds are the capital F's. The little f's are the forward rates. And forward rates, when you took Intro to Finance, you calculated. It was usually a part on the as you're doing discount rates and yield curves. There's a part where you calculate forward rates. The forward rates are the things that we're used to. Here, what we're going to do is throughout assume continuous compounding, which is much easier to work with than discrete compounding, and it can be done without loss of generality here. So that's kind of the setup of the notation, that what we're going to be doing is splitting up any bond that we see that goes from 0 to K or 0 to T into a shorter component and then a longer component. And we're going to see how that longer component evolves as we get closer to it starting. So first, a little bit of a digression. about normal distributions and log normal distributions. A normally distributed random variable with a mean of mu, and the mean is the expectation of x, and a variance of sigma squared, is often referred to in shorthand as x is distributed normally with a mean mu and variance sigma squared. If x is normally distributed, then the expectation of e to the x, or e to the minus x, has the property that it's going to be e to the minus mu plus 1/2 sigma squared. And that very simple expression is going to drive most of our results. And the reason is that when we start talking about the forward rates as opposed to the forward prices, we're going to say the forward rates are normally distributed. And so when we go to calculate prices of bonds, we're going to be using the discounted value under continuous compounding, so e to the minus little f, to be colloquial about it. Okay, so once again, the adjustment term is there's an adjustment term because of the first moment of the inverse of exponentiated forward rates. That's a fancy way of saying the expectation of e to the minus x involves a variance term that's not in the forward price. And so our initial relationship is that the forward price is the expectation of e to the minus f being the forward rate. And so that expectation is not just the forward rate, but has a variance term. So if we take initial spot and forward rates, we can decompose any instrument into its subcomponents, shorter components that exist. And so we'll start, what we're going to do is we're going to start with 1 period increments. And we're going to spend the first third of the presentation talking about just evolving from period 0 to period 1 for anywhere on the curve. Then what we're going to do is talk about evolving from period 1 along the curve to period 2 or period 3 along the curve, or as the curve moves through time. And then the last thing we're going to do is start to shrink the time periods down from a one year increment or a 1 period increment to a smaller increment, so we can get closer to the continuous time models that HJM use. So what we want to do is start with some just algebra of rates and forward rates decomposition. And so you could write, for example, R03, once you've taken logs of the pricing function, the e to the minus function, you've got R03 can be decomposed into 1/3 of the forward from 0 to covering the interval 0 to 1, plus 1/3 from the interval 1 to 2, plus 1/3 from the interval 2 to 3, which is also the same as 1/3 of the interval from 0 to 1, plus 2/3 of the interval from 0 to 3. I didn't write it here, but it could also be written as 1/3 of the interval from 0 to 2, and then 1/3 of the interval from 2 to 3. So you can play around with the forwards that you're looking for. You can play around with the information that you've got to see which forwards you need to find. But generally, you're able to find the forwards at the initial starting date very simply. And so in discrete time, if we're using the regular discrete terminology, we've got a rate out to period n, and the nth period rate decomposes into a j period rate where j is less than n, plus a forward rate, or times a forward rate. And so all that is the stuff of standard decomposition that you do in finance in the intro class. And you can find the forward rates at period 0 simply by taking the n period rate, 1 plus the n period rate compounded for n periods, divided by 1 plus the j period rate compounded for j periods, all that to the 1 over n minus j power, subtract 1, and you've got your forward rate from period j to n. And this is the kind of question that you ask on an exam in an intro to finance course. It's the easiest question for a faculty member to write. And it's a good differentiator between the students who have kept up with the material and those who haven't. But you do this so many times that you start to lose track of asking the question, okay, once you've got this forward rate, then what? And so we're going to spend a lot of time today on the then what. In continuous time, it's an even simpler process because the arithmetic just works out easier. And so we'll be playing around a bit with that. And you can see that in a algorithmic sense here, notational sense here, where if we look at the 2-period price, we could write that as the e to the exp of minus 2 times the forward from 0 to 2, period 0 to 2, and we could decompose that into the forward from 0 to 1 and 1 to 2. And so it becomes they're additive in the exponent, so it's very easy to play around with continuous discounting. It's much easier to play with continuous discounting than discrete discounting because the arithmetic just is simpler to work with. All right, so what I want to do now is we're actually not going to take the respite yet. What we're going to do now is flip to the switch screens to the Excel. Let me bring up the file first, and then I'll share the screen. Let me share the screen again. This is something I do in class, and I love to play with this in class because it gives an idea to the students of what's going on. So first, we've got our bond convexity. We see that picture. So this is based on some treasury information that I downloaded a year ago. Now, we are doing some cheating here. Let me talk about the cheating for a second. Usually what we're trying to do is to price a market curve. So here, I'm just using the treasury curve as if that's the trading curve for interest rate derivatives and swaptions and all that. And actually a slightly different curve. And that curve relies on things like secured overnight funding and swap rates rather than the treasury curve. There, within a bank, there are a bank maintains the trading operation and rates maintains several curves. There's a curve that's for tax exempt. There's a curve for treasuries. There's a curve for single A credit, which is basically the bank to bank lending rate. And so those are the rates that are just domestic rates. And then there's the whole gamut of rates for other countries, whether onshore rates or offshore rates, different yield curves. So a bank maintains dozens of yield curve. A large multinational bank maintains dozens of yield curves, and we're just pretending that the treasury yield curve is the yield curve that we're going to use. Here we're doing it for a numerical example, so you can see how we build the yield curve. We start with the yield curve that we downloaded from. I downloaded, these are treasury data based on different maturities. We've got 1 month, that's 1 over 12 is 0.08. And the yield was, at the time I downloaded it a year ago, was 2.93%. So just a little under 3% here. Let me expand that out a bit. And one thing about doing these presentations in Zoom is that there's some task bar that covers up everything that you're interested in doing. Wherever you are, there's a task bar covering it up in a way that you don't want it to. There we go. So that lets us take the yield curve, which we plot directly, and then using the standard arithmetic that we use in finance, we construct the forward curve using that formula that I showed you a moment ago. Now, for risk purposes, and this is one of the big things, and this is one of the reasons I love showing this in class, is that one of the important things about doing risk, whether you're on the trading desk or risk management, is that when you're doing risk on yield curves, you can't simply shock the yield curve unless you're shocking it in a parallel way. So here, the orange one is the yield curve, gray is the forward curve, and yellow is the shocked yield curve. And it looks fine because I've got a parallel shock here. The yellow line, the yellow area is the shock to the yield curve. But suppose I only want to shock one part of the yield curve. Oops. If I only want to shock one part of the yield curve, say 1 point on the yield curve, if I only shock that 1 point, I create the appearance remember this yellowish curve is my reconstructed yield curve after the shock. If I only do that shock at one spot, it creates this illusion of an arbitrage opportunity that would never exist in the real market. Because in the real market, if interest rates went up at this point, this bond would be much cheaper. These two bonds would be more expensive. And with a combination of the two more expensive bonds, I could completely replicate the duration of the cheap bond, and so it would be where you would buy low, sell high, as much as you could, and capture that differential. That's not quite a pure arbitrage because that's a duration matched arbitrage, Um, but that's effectively what you do. And you could even narrow down further because it's only at that point. And so if we shrunk the window, this would be more of just a spike upward at that one point. And that's how using instruments of very short differential, you'd capture it. So we can't simply shock the yield curve itself when we're doing risk, either as risk managers or if you're on the trading floor. You can't simply shock the yield curve to see how that would affect your position. What you have to do is you have to shock the forwards and then recalculate the yield curve based on the shocked forwards. And when you shock the forwards, so here the coloration on the graphing differs. The original built back, so the original yield curve is the blue line. The orange line are the shocked forwards, and the gray line is the shocked yield curve. And so let me put a much bigger shock here in the yield curve, in the forwards rather, and see how that changes the yield curve. So it's a big shock to the yield curve, but it shocks it in a way that doesn't create the arbitrage opportunity from before. It's a 10% curve. Short of a nuclear war, I don't think you'd ever see a 10% shock. And so what happens is as you shock the yield curve, as you shock the forward curve rather, you're getting a smoother adjustment in the yield curve that doesn't create the arbitrage problem that just trying to shock the yield curve directly does. So that's why in risk, we're always interested in what's happening to the forwards. And by risk, I mean both risk managers and traders. You're always interested in what's happening to the forwards and watching the forwards because it's the forwards that drive the yield curve and changes in the yield curve. And it's through those forwards that you can understand your risks, do hedging, etc. And then finally, if you wanted to, and this is something for class, but I included it here. When you shock a yield curve by shocking the forwards, if you had the price of any bond, it would change the price of the bond. So here I've built this little, make-believe 10-year annual bond with a coupon rate of 4%, and the original bond value at the original prices, at the original discount curve is 106,245. But when I shock the forwards and hence derive a shock to the yield curve, the price, and I do that only at the 2-year mark, the price of the bond drops by $9.81 per unit. And so I can assess valuation changes of my instruments here. I've got a bond, but it could just as easily be a caplet or a swaption or any instrument. I just take the yield curve, build a pricer, and once I've got the pricer, I can shock the forward rates, derive the shocked yield curve, and revalue all my instruments that way. And that's essentially what's happening on any trading floor and in any risk management department. It's just happening on a very large volume of instruments, and it's not being done in a spreadsheet with a dinky little bond. So that's the first part of what I wanted to cover. So what I wanted to do was to let you play around with this. Take about 10 minutes, spend time on this first page, spend time on this third page, and see if you can change to, so everything here works for discrete rates, discrete compounding. It's a pretty simple process. In fact, it simplifies things quite a bit. If you change to continuous compounding, but what we're going to do now is take about 10 minutes of a little bit of a break and have you walk through it, in a breakout group or by yourself, and play around with it and have some fun. So it's 1:40 now. Take 10 minutes. If you have to use the restroom, it's a good chance to use the restroom, get a cup of coffee, but then play around with that spreadsheet and see about changing it to, spend 5 minutes understanding it, and then a couple of minutes to change it to continuous discounting. And then we'll pick up again at 1:50. Any questions before we do that? All right. And when we do pick up again, we're going to go straight to the HJM evolution process, and things will pick up speed from there. Okay, welcome back. Let me go back to screen sharing and we'll jump right into what we want to do. All right, so that covers we've covered the preliminaries. What I want to do now is start working through the Heath-Jarrell-Morton evolution of rates. And within a very short period of time, two things will happen. One, you'll start to understand how rates evolve, how the rate evolution process works in the Heath-Jarrell-Morton model. And the other thing you'll start to feel is that arithmetic is really boring. So, but hopefully not. The boringness is taken away by the fact that understanding the evolution of forward rates is really kind of a fascinating thing. And so remember, all we're using is the convexity. That's what's driving everything that we're doing. And so if we start with a 2-period bond, we can decompose it into a 1-period bond and then a 1-period bond that starts 1 period from now. So we've got our 1-period bond, and that's what I'll call P01. And then we've got a bond, the forward on the bond that goes from period 1 to 2, and that's capital F012. So if we were to write that out in the exponential notation, that would be the price of the discount bond today plus the forward from of today covering period 1 to 2. So we can do some arithmetic, some algebra, and rewrite that as today's forward for the discount of the forward rate for that bond. But given what we know about forward rates, given what we know about log normality, that little bit that we know, we know that forward rate has to be equal to the expectation of the forward rate next period. And that tells us that when we work through that algebra, that tells us that the forward rate for next period is the forward rate covering period is the initial forward rate plus an adjustment term, which is 1/2 the volatility squared. That is the volatility covering period 1 from 1 to 2, plus the error for that part of the curve. And that error component I want to focus on for a second as the error that occurs at period 1 that covers the 1 to 2 period of the curve. So that's the innovation of that one part of the curve. And that may be the same across different parts of the curve, but here we've got an error term, a random component for period 1 covering the 1 to 2 slice of the curve. And so this evolution of our forward rate tells us, again, the forward rate for period 1 to 2 that we expect to obtain at period 1 is the initial forward rate plus an adjustment term plus an error component. So you can think of this as mean plus error. And that forward is coming from the no arbitrage relationship. That's a little bit different than saying that that's the expectation of future rates. We're not quite saying that the expectation of future rates is the same thing. It's only under risk neutrality that expectation holds for rates. But it's a Sorry, I lost my place. Subtle distinction, but we want to note that. And also, you want to note that as we move through time, the curve that we're looking at is a little different. When we look at the curve today, we're looking perhaps out 30 years. When we're looking at the curve tomorrow, today's part of the curve dropped off. So the curve drops off the current date, but adds on a slightly longer date. So we're not holding the curve steady. We're letting the curve move through time as well. Right now, we're only going one period forward. But ultimately, we want to do that. So to see what would happen if we go 2 periods out. So now we took the curve out to period 2, and we found the forward rate covering period 1 to 2. Let's look at the forward rate covering period 1 to 3. Well, the forward rate covering period 1 to 3 would be the price out to period 1, and then 2 times the forward from 1 to 3. It's 2 years, which would be 2 times the mean and 2 times the error from 1 to 3. Which when you do the arithmetic, tells you that the forward from 1 to 3 starts out with the initial forward, no surprise there, plus the variance adjustment term, plus an error from 1 to 3. So now I want to make a couple of points clear. Right now, this is a 2-period volatility term. So it's not the same as the 1-period volatility term before. And this is 2 error terms. This is the error term from 1 to 2, plus an error term that would cover the period 2 to 3. And we're going to decompose that in a moment. It should all pretty much look the same, except now we're covering a window that's 2 periods long instead of 1 period long. So our multiplicative terms change. There is a question in chat. We're going to talk about Sabre. No, not really, because that's a very specific model for estimating volatility, 2-dimensional volatility surfaces in particular. And so that would be more appropriate for like an equity volatility, stochastic volatility discussion. So we're not really going to talk about that today. Okay. Okay, so we've got a 2-period process that we're looking for now. And we've got our 2-period volatility and our 2 error terms, our 2 innovations. So if we did expand on the sigma squared 113, so that's the volatility covering periods 1 to 3. We have that we could decompose the forward from 1 to 3 into the forward from 1 to 2, plus the forward from 2 to 3, plus 1/2 the volatility, I'm sorry, 1/4 the volatility from 1 to 2, 1/4 of the volatility from 2 to 3, and 2 times the covariance of the interaction between the two innovations that occur on the curve between 1 and 2 and 2 and 3, plus the two innovations. So here we allow for 2 innovations, and the forward from 1 to 3 in its most general form, and most of the time there are variations of HJM that are meant to reduce the number of factors, but here we've got arbitrarily many factors to start with, and so we've got 2 factors for 2 forwards, plus the adjustment term, that's the variance of the sum of the forwards, plus the 2 innovations. And so we view the primitive errors, those innovations, as relating to the 1 period forwards. Again, in a single factor model, like say the whole Lee model or the Vasicek model, or any number of single factor models, you'd be able to reduce that volatility term based on the number of factors, but we want to allow for as many factors as we can for now, because we can always reduce later. With respect to forward rates at day 1, the forward rate covering those 2 periods, periods 1 to 3, is linked to the 1 period forward rate realizations that go from 1 to 2 and from 2 to 3. And so what we're able to do, what you're going to see in a minute, is what we're able to do is to take that 2 period forward rate, and we already know the 1 period forward rate from the previous slide, and so we're able to find the forward rate for periods 2 to 3 at period 1. So F123, we're able to find that one simply by doing subtraction. And we'll see that in a second. But it's through that sort of process that what we can do, so we've now moved out to period 1, we can do a 1 period rate, we can do a 2 period rate. From that 2 period rate, we can derive the second 1 period rate, because we already know the first 1 period rate. And through that same sort of process, once we've got the 1 period rate from period 1 to 2 and the 1 period rate from 2 to 3, we're going to see in a minute that we can find the 1 period rate from periods 3 to 4. If we do a 3 period, if we go 1 to 4, that's a 3 period rate, and we'll be able to get the 1 period rate from 3 to 4. We could go on and on all day long. Once we get to 4, we're going to generalize. And so what we can see is that because we know that the forward rate from period 2 to 3 is the same as 2 times the forward rate from 1 to 3 minus the rate 1 to 2, we can calculate the 1 period forward rate from period 1 to 3 just by subtraction of the 2 period forward rate minus the one that we already calculated first. And so that iterative process of expanding by increments and then doing some subtraction allows us to calculate that the 1 period forward rate from period 2 to 3 at period 1 is the initial forward rate plus the half the variance from periods 2 to 3, plus a term that depends on the covariance between the innovation from 1 to 2 and the innovation from 2 to 3, plus its own innovation. So it's very much the fact that we're able to do this iteratively, that we can very quickly recap things as having the forward rate from period 1 to 2 is just the initial forward rate plus half the variance plus the innovation. The forward rate from at period 1 from covering 2 to 3 is the initial forward rate plus half the variance plus a covariance because there's a previous period on the curve that has its own innovation, and those innovations may be correlated, plus its own unique innovation. And the 2-period forward rates, of course, are from 1 to 3 is the initial one plus half a quarter of the cumulative variance plus half each on the innovations. So let's put some intuition on this. Economics of what's going on is that there are for a 2-period bond, there are 2 sources of risk. There's a risk that can occur in the first period and a risk that can occur in the second period. Those risks may be correlated, so the total risk of the instrument reflects the sum of the 2 sources of uncertainty, and of course any correlation between those sources of uncertainty. When we start to take those apart into the 2 components, we can see that and hedge away the risk of one versus the other. You can see that if we take away the risk of the movement out to period 1, there's and simply focus on the forward from period 2, there are still some volatility sources that matter. One is the covariance between the innovation that occurred in period 1 and an innovation that occurs in period 2, and then of course the innovation that occurs in period 2. So there's even if you take away the first one, there's still that correlation that still lingers. And let's just take this, we'll take this one more step. And when we take it one more step, then we'll just generalize. And this part should be clear of how to move from period 0 to period 1 anywhere on the curve. So to go from period 0 to period 1 out to period 4, that's a 3-period bond that goes from period 1 to 4, which can be written as the 3 forwards as a function of the 3 forwards, the forward from 1 to 2, 2 to 3, 3 to 4, all at period 1. So that's 3 terms. And the volatility term adjusts accordingly. So what we end up with is the 3 periods from period 1 to 4 at period 1 will be the 3 times the forward from 1 to 4 at time 0, plus 9/2 of the volatility covering that 3-period window from 1 to 4, plus the 3 innovation terms. There's an innovation possible at period 1, an innovation possible at period 2, and at period 3. So when we do that, and we already know how to get F112, and we know how to get F123, so we can get F134 as the subtraction of these two terms from F114. And when we do that, we see that the forward covering period 3 to 4 has an adjustment term, and that adjustment term for periods 3 to 4 is half the variance of 3 to 4 plus the covariance between the first innovation and the final innovation, plus the covariance between the second innovation and the third innovation. Oh, there's a typo. I should say 134. Proving the disclaimer at the beginning that the probability is 1. There's always a typo. So what we see now is that when we did the forward from period 1 to 2, we had the initial forward plus half the variance and an innovation. When we did the forward from periods 2 to 3, we had the initial forward, half the variance plus 1 innovation, plus a covariance plus 1 innovation. And now we've got the two trailing innovations may matter in the sense of their covariance. And that brings us to our general rule that we're going to do formulaically in a second. But first, let's just look at how it looks as we build out the forwards. And so if you look at these 1 period forwards, you can see the pattern that's developing. And that tells you how to build out anywhere along the forward curve, get the 1 period forwards for anywhere along the forward curve. And what you see, one of the takeaways that you should get from this is that the variance terms that accumulate, the adjustment terms are accumulating. And so the adjustment is getting larger the further you go on the curve. Or more involved as you go further on the curve, I should say. And so if you want to put this into matrix notation, you can write out the period for the formula for the long forwards as t times the forward from little t to t plus 1 is the forward from, actually this should say 1 rather than little t, from 0 to covering the window little t to big T plus 1, t squared s, where s is a vector of 1s, omega, the volatility matrix, s over 2, plus t times the errors. Or the way I think it's preferable to think about it is the forward from period 1 covering period t to t plus 1. The short forwards are given by the initial forward, so calculated at time 0, plus a volatility term, plus the sum of the covariance terms, plus the innovation itself in that period. So this formula right here at the bottom is really fundamental to the pricing of short forwards for the HJM model. We've reduced the problem to algebra, to arithmetic really, And it's not all that difficult when it's done as arithmetic. It's just a little bit tedious to go through the arithmetic. And so I would encourage all of you to do it. And this is something though that's very simple to implement in a programmatic fashion. So that covers the basics. We'll before we go on to an arbitrary period, instead of just stepping forward from 0 to 1, we'll step forward from 0 to arbitrarily far. But before we do that, let's just look at a couple of special cases. There are two models that are used consistently in pricing instruments. And we want to come back to these later. But one is where there's a single source of uncertainty, a single source of volatility. That's called the whole Lee model. And so there the covariances are all the same. They're all just equal to the variance.
I didn't get that. Could you try again?
Sorry, my watch listens to me and thinks I'm talking to it. So the whole Lee model is the simplest model, and that's just a constant volatility model, single source of uncertainty. All the correlations, the covariances are identical. The Vasicek model is a single factor model, but it's a slightly different version in that it's the same innovation that affects all parts of the curve further out, but the innovations dampen. So there's a shock to the front of the curve, and that shock propagates through the curve, but in a dampening fashion. And so the shocks are mostly to the front end of the curve. We'll come back to this later. But those single factor models are very common simplifications of the HJM framework. The HJM framework was written, if you go through the original paper, it was written in the most general framework, which is what we're going through here. And then at the end of the article, it reverts to the special cases to show examples. But as I've said, it's a very dense article, very hard to read. All right, so what we've done is we've stepped out along the curve. And what we're going to do now is step the curve forward. So the first step was to step the entire curve out one step and see how different points on the curve would move as we made one step. Now what we want to do is think about, well, what happens if we start making lots of steps? What happens to the front of the curve for lots of steps? What happens further out on the curve for those lots of steps? So we're going to look at that. And then after we look at the curve moving, not just moving along the curve for one step, but then moving the curve itself across different steps, then we're going to start shrinking the time steps down and get to closer to the continuous time model that sometimes gets implemented as a, well, certainly when it comes to caplets, caps or caplets, those get implemented as continuous time versions. Other instruments, you stay with the discrete version. Depends on the analytics that are required. All right. So what we want to do is step forward now from period 1 to period 2. So the way we did it before was we stepped out from period 0 to 1, 1 to 2, 2 to 3, 3 to 4, all at time 1. Now what we want to do is step from time 1 to time 2, time 2 to time 3. And so now what we want to look at is the forwards at time 2 and play with that. So if we want to find the forward at covering periods 2 to 3, it's recursive. It's the forward from period 1 covering 2 to 3 plus half the variance. The adjustment is half the variance from 2 to 3 plus the innovation at period 2 covering the window from 2 to 3. So combining that expression with what we have for F1, 2, 3, again, it's an arithmetic problem. The forward from period 2 covering period 2 to 3 is the initial forward F0, 2, 3 plus half the variance covering periods 2 to 3 from period 1, half the variance from periods 2 to 3 plus the covariance between 1, 1, 2 and 1, 2, 3, those factors, those errors, plus the innovations at period 1 covering period 2 to 3 and the innovation at period 2 covering 2 to 3. So what we can see now is that it's a little bit different. What's different is that the volatilities are collecting and the errors are collecting through time. So we've got the volatility from period 1 covering 2 to 3 and the volatility from period 2 covering period 2 to 3. So there was, and to think of it, we expect an innovation at period 1 and we expect another innovation at period 2. Random shocks are happening every day. So as we get those random shocks, as we have possibilities for those random shocks over the different periods, the further we project out in time, the more those random shocks are going to accumulate. And so it's not just the covariance term across different points along the curve, but it's the innovations that occur through time as the curve moves through time. So now there's two sources that are affecting things. It's really kind of fun at this point. Similarly, if you want to find the forward covering period 2 at period 2 for covering periods 3 to 4, it's the forward from period 1 to 3 to 4 plus half the variance at period 2 plus the covariance from 2 to 3, 3 to 4 plus the innovation at period 2 covering the fraction of the curve that goes from 3 to 4. So if you want to find the forward from period 2 covering period 3 to 4, it's going to be the forward covering period 1 from 3 to 4 plus half the variance of at period 2 covering the window 3 to 4 plus the covariance at period 2 between the window covering periods 2, 3 and 3, 4. And then there's the innovation in period 2 that occurs on the window 3 to 4. But you already know from before that the forward at period 1 covering 3 to 4 is the forward at time 0 covering 3 to 4 plus the rest of the stuff in red. So you already know that. And so you can collect the terms. And now what you see is that the forward covering period 2 over the window 3 to 4 can be written as, and this is a long sentence to say, but you're getting the pattern now. The forward from period at period 2 covering the window 3 to 4 is the initial forward at time 0 covering that window, plus half the variance at time 1 covering 3 to 4, half the variance at time 2 covering 3 to 4, plus the covariance between at time 1 of the innovations between 1 and 2 and 3 and 4, plus the innovations at time 1 covering 2 to 3, 3 and 4, plus the innovations at period 2 covering 2 to 3 and 3 to 4. Plus the 2 innovations themselves. So that's enough to start to see the pattern developing. And what we're getting to is a much messier equation, but really it's just the effect of aggregation and doing some arithmetic. So as we write it out, what we want to do is, to simplify things, we define a term called alpha. And alpha's half the variance from t to t plus 1 plus the sum of variance terms, and that lets us write the forward at time t, the short forward at time t, so it covers the window t to t plus 1 as the original forward, plus the sum of alpha terms covering period j from 1 up to time t, which is little t, plus the innovations themselves. So the forward at the short forward at time t is the initial forward plus the sum of the alpha terms as they collect, and the sum of the innovation terms. So, the intuition is that this last part is that there are more innovations happening on that slice of time as you go through time. So, if you're going out 5 periods on a slice of time, there are five events that could have occurred, 5 innovations, 5 days of trading, 5 one-year periods where things happen to change. Things happen to change rates, and the adjustment term has to take into account the volatility of that in order to keep it no arbitrage. Okay, so this part is a relatively, let me go back through this for a second. This part is relatively straightforward in that you start to realize that, gee, a lot of what we're doing is just arithmetic. It's detailed arithmetic, but it's really just summing things up. And so all we're doing is maintaining the no arbitrage relationship, but maintaining that the forwards themselves are normally distributed so that when we exponentiate them, we have the adjustment term, but the adjustment term is simply reflecting that the variance is growing as our window grows, or as we move further out in time. But it's really remembering, where is it? If you, sorry, I'll find it. Yeah. If you remember this at the bottom of page 14, this is basically everything that we're talking about today. It gets a little more involved, a little more complicated about what this term comprises, or what this term comprises. But what we're really talking about is the initial forward plus an adjustment. Again, it's an adjustment that gets uglier and uglier, plus an innovation that gets a little bit uglier. And if you just keep this in mind, almost all of this makes a lot of sense and gets much easier. All right, so before we go any further, let me stop for a minute and see if there are any questions. Because we're covering, I mean, it sounds like it's very simple. But it's not quite as simple as I'm making out. So all right. Let's see. All right, so let's go back. Not seeing any questions. We're gonna have another breakout in a few minutes. But now let's start to shrink the time steps a little bit. So the first thing we're gonna do is shrink the time step from delta 1, that is a time step is one full period, to what happens if we shrink to half a period. And then once we get to half a period, we're gonna make delta just an arbitrary time step. So again, we start with F112 is F012 plus sigma 1 half sigma 112 plus E112. So the initial forward plus adjustment plus random component. Now if we start with going out half a period, let's find the forward that covers the 3/2 period from period 1/2 to 2. Okay, so now we're covering 3/2 of a period, the period from 0.5 to 1, from period 1 to 1.5, and from period 1.5 to 2. So instead, when we used to go out 2 periods, it was 2 periods. Now it's 4. We've divided it into 4 intervals. And what we see is that it looks a lot like what we were doing if you go back to the 3 period forward that we did going from periods 1 to 4, only now we're going from periods 1/2 to 2. It looks like the same formula. The difference, there are two differences. One difference is that it's only 1.5 periods in total length. The other difference to keep in mind is that these innovations now cover, so it's not the full period's innovation, but the period is now half a period long. So that we're having a shorter window for an innovation. So those innovations are likely to be smaller than an innovation for a whole period. So we're breaking things up into smaller units of time. More terms are collecting, but they should be smaller individual components that are collecting because we're shrinking the time window down. So notice that the results depend on the width of the interval t minus delta, so how big the interval is, but not on the width of the interval itself. Okay, so each shock now has a smaller impact window where it can occur, and more than likely a smaller individual effect. So this gets really messy, but given that we have that the error term from 0.5 covering the 1.5 period window from 0.5 to 2 is really 3 error terms. That is the innovation from 1/2 to 1, the innovation from 1 to period 1.5, and the innovation from period 1.5 to 2. We can expand out our expression of the forward from period 1/2 covering the window 1/2 to 2 as we could keep it simply as 1.5 times the forward covering that window plus 9/8 of the volatility covering that window plus 1.5 times the cumulative error across that window. Or we could write it out in terms of its components. And what we want to do that because we want to get the individual time step components. So we do that in this case, and we can see the individual time step components. And then we start to near the home stretch of seeing how this sum is going to change. And what we want to do is get the short forwards for delta 1.5, then get the general rule for an arbitrary delta, then we shrink the delta, and then we circle back to a factor model. So we're extending out through time. What we're doing now is shrinking the deltas. And so what we've got is the starting with that 3-period delta. We can find the delta. I'm sorry, we can find the forward covering the period 1.5 to 2 as the original value plus 1/4. And we do a ton of subtraction as we do this. So we get the original forward plus an adjustment term. The adjustment term is half the variance covering that window. I'm sorry, a quarter of the variance covering that window, plus 2 times the covariance between the innovation from 1/2 to 1 times 1/2 plus, and the innovation from 1.5 to 2, plus the covariance between the innovation from 1 to 1.5 and 1.5 to 2, plus the unique innovation over the window 1.5 to 2. So that's a lot to say. And that's a lot of subtraction. What we get when we get to the first step generalized is that at the first step, at time delta, it's the original forward plus delta times this alpha term, which is the sum of which is the variance, half the variance of the short forward t to t plus delta, plus the sum of the covariances plus the innovation for that term. So note again that the adjustment term represents a sum. But what we have is the original forward plus an adjustment term plus an innovation. It's the same thing over and over again with a funkier looking terms. So in the general case, if we want to find for an arbitrary time step t, it's going to be the original forward plus the sum of those deltas out to period t. So we're going to have to step out, just as we had to step out from period 1 to period 2, from period 2 to period 3. Now we're stepping out in delta units, and those adjustment terms are going to accumulate. Oh, another typo here. Those adjustment terms are going to accumulate. And if you want to see it in its full gory detail, it's the adjustment curves going out the curve and then going out the time steps. So how many times? So the first one is how many steps forward along the curve are you going? And then the second one, the outer one, is how many time steps forward are you going through time? So for inside is across the curve, outside is through time. And to me, this is just one of the coolest things that you can start to visualize, because now you see the curve in your head. What you should see is the curve collecting terms through time, and then the curve itself moving through time. And that starts to get to be a nice representation in your head. And of course, you've got more things that are happening through time. Affecting the part of the curve that you were looking at. So as you collect these terms, you can think that if these terms, one of the things I want to focus on here is some intuition, and it may not look all that intuitive, but if you focus on this and think that in general, the shocks tend to be positively correlated, so this covariance, these covariances will be positive. If the shocks are positively correlated, what it means is that generally as you go through time, and the further out on the curve, the more shocks there are that can happen along the curve, and then there are shocks through time, what you end up with is no matter what the shape of the curve was initially, downward sloping yield curve, perhaps initially, as you go through time and at the back end of the curve is very much likely going to start to slope upwards in a way that's meaningful. So you go from an inverted curve, any inverted curve, and have shocks that are positively correlated in a multi-factor model. It means you're definitely going to have, if you project far enough out, you're definitely going to have an upward sloping yield curve as your not necessarily as the realization, but as the no arbitrage forward price for that curve. The implication is that go far enough, and the no arbitrage models will always imply that the long end of the yield curve, if you go far enough out, the long end of the yield curve will always be upward sloping at some point in the future. I think that's just a very cool result, and I'm sure this is what I'm sure of, but I've never explored it. I'm sure that means that there are arbitrage opportunities at the long end of the curve. Because it's a facet of the model that may vary from the realization in the market. Maybe it's not arbitrage, but it's a reasonable risk position to take, because the model is always telling you that the curve is upward sloping, even if you have reason to think that the curve at that point may not necessarily be upward sloping, or at least as upward sloping as the model would suggest it is. It's the difference between markets and models, often that are where traders make their money. So I think of that as something that you want to think about. So let me take another break here. I have to plug in my laptop for a few minutes. And we'll pick up again at 12 minutes. We'll pick up again right at 3 o'clock and finish up the bits of it, open up for discussion, and talk about extensions and pricing. All right, so let's take a break. I'll see you in 11 minutes. Oh, welcome back. All right. So I'd say it looks like everyone's back, but everyone's blacked out, so I can't see, which is normal for these things. So let me go back to sharing the screen. We can start talking about implementation now and actually using it. So we've gone through quite a bit of arithmetic algebra to understand it. What we're going to do now is finish up with the modeling part of it, and then get into some discussion about how to use it and what it's good for. So let's step back just a couple of pages. Again, we're now looking at the arbitrary delta being the driver, and this is the first step out, has this adjustment term. And so if you were to try to implement this, what you would want to do is implement this adjustment term, and you'll need to put some factor structure here between the factors. So we're going to talk about that in a few minutes. And then as you step through time to an arbitrary time period, little t, you've got to take those adjustment terms and then sum them through time. And so there are two sums that have to be done. One thing is as we get to this point, we could start to talk about differences between. So what you can do now is think about what happens as the time step shrinks down, and this becomes a continuous time model. So one thing that happens in the continuous world is that this term, as you shrink delta, this term goes away because it's delta times a variance that's shrinking down in time window. So that part goes away, but this part doesn't go away. So the sum, which instead of it being a sum from j equals 1 to n, becomes an integral over the time window, 1 to n. This inner sum becomes a sum over factors, and this outer sum is the sum over time steps, or the integral over time steps. So the inner part is a sum over factors, and the outer part is an integral over the time window. And that's what you see in the model. And let me let me stop this share for a second. I used the time before to try to put find it again. For just a second. Let me share this window. This is an ugly window, but I'm going to share it anyway. So this is from the Heath Jarrow Morton article. The rendition that I have on screen is pretty brutal, but gives you the idea. And so if you look, what you can see is the integral over time t for the alpha term. So that's the accumulation term. And then the sum of the factors over the integrated over the time window. And so it's messy, but it's the same as in the article. Or maybe this is I'm not sure this is a better way to see it, but anyway, I would encourage you to take a look at the article if you're interested in it. It's a very good article. You can get it online at the library. The library has it in several formats. I had a cleaner format a few minutes ago, but somehow I managed to move away from it. So let's go back to the presentation. So this is where we were. Now, so let's look at this for a minute to think about single factor models, because the general case may be, sort of nice, arithmetically pleasing to play with and all that, but it's less practical. No one has more than in practice, you don't find more than 3-factor models. Most are 1 or 2-factor models that you see in practice. And so what you want to think about are the simplifications involved if we jump to, say, single factor models. And so in a single factor model, the covariance between any two components, so I've got ijk versus xyz, will simply be the product of the standard deviations, and the alpha term can be written as the innovation, the volatility for its own at any delta. The alpha term can be written as the volatility for its own volatility over its own little window, t to t plus delta, plus the sum of the product of the standard deviation of that own window times all the windows previously. And then of course you'd sum the alpha across deltas to get to time t. So under Ho-Lee, which is the very simple single factor model, what you end up with is delta sigma squared t plus t over delta sigma squared, which really, when you shrink down the deltas, this part that's highlighted goes away, and all you're left with is a variance that's increasing through time. But there are variations of this where So this is constant. This is a single factor along the curve, and then it's a constant variance through time. And so you could easily think of variations of this where you've got, so for example, the Vasicek case, where as you go along the curve, you get a dampening effect of the variance. So instead of summing the same number t times, it would be the sum of an exponentially decreasing function, for which there are series approximations or series sums. And the other thing is that through time, the volatilities there may be some time evolution of the volatilities. So you think of perhaps volatility, the base volatility through time having some normal level of volatility and some variation around the normal level of volatility. So there are things you can do with the Holy model that or the Vasicek model that don't take you out of the single factor world, but give you sort of a richer flavor than call this the dumb Holy model. Richer flavor than the dumb Holy model. The dumb Holy model says volatility is always the same, no matter how far you go out on the curve. Everything bumps up and down the same. And no matter how far out in time you propagate the curve, the volatilities are always the same. So you can tweak those. And that's what there's a working paper by Peter Carr. I can't remember Yang's first name. If you ever have time, so Peter unfortunately died last year. But if you ever have time, he died. So short digression on Peter Carr. Brilliant guy, nice guy, very prolific in the academic world, and also prolific on Wall Street. And he kept going in and out of Wall Street from Wall Street to academia, academia to Wall Street, back and forth. And he did that several times. But one of the things he did, and most of you are probably too young to have kids, but one of the things he did is he founded the Museum of Mathematics, helped found the museum, not solely, but helped found the Museum of Mathematics in New York. And it's just a great museum. And if you have kids, you have to take them to the Museum of Mathematics at some point. But as I said, unfortunately, Peter passed away last year, very young, but tragic. And so what Carr and Yang showed was that any single factor model has this form, but you can do lots of things with this where you're putting structure on the form, so it doesn't look like this sort of arbitrary accumulation term. You can have structure on this where, where, like I said before, where the volatility is changing through time, but it's still a single factor. So within any time slice, there's correlation among the disturbances on the curve. And through time, it might follow a nice format. So what that tells you, what that gives you is a richer set of possibilities. And so whenever you're implementing these in practice, there's a trade-off between practicality. You want a model that's simple and practical and that traders can use, so it's got to have just a few dials, but you also want it to capture the dynamics of the market. So the trick is to try to find the simplest model that lets you capture the relevant dynamics of the model without having to recalibrate every day or, you know, every couple of days. You don't want to have to recalibrate too frequently. That tells you that your model, when you have to recalibrate frequently, that tells you there's probably something wrong with your model. And so you want to find versions of this where they're not quite in gory detail of having the full flexibility, but they become useful because it's only got a simple number of parameters. So someone asked a question about Sabre models earlier, and you know, one of the advantages of Sabre models is that it's just 3 parameters for a volatility, for stochastic volatility model. So that makes it usable as opposed to a general stochastic volatility model, which could have many factors driving stochastic volatility. So that Occam's razor of finding the simplest explanation becomes doubly true, not simply as a matter of science, but as a matter of practical application. If there are too many dials on a model, it's not usable. And that's something that quants struggle with, especially with traders, is trying to make a model both usable and capture the relevant dynamics. So we've gone through sort of the basics of Heath Jarrow Morton, but it's, like I said at the beginning, it's a model that has been enhanced or supplanted. I'm not sure what the right word is. Many features of Heath Jarrow Morton are still used as they were written, so it's not that it's been tossed or anything like that. But there are extensions where there's a recognition that things are different. And so one of the things I wanted to spend a little time on today was talking a little bit about the frame of reference that we've been using, and how different models look at it. And so what we've been doing today is marching from today through time. Everything that we've done today is all looking forward from today. And that gives rise to obtaining the forwards by walking forward through time. But there are other modeling approaches using existing prices for instruments like caplets, or even though it's not used anymore, it's called the LIBOR model, and I'll talk about that in a minute. And the grandparent of using what's called the forward measure is called the BGM model. And so I'll give you, there's a reference here to the BGM model that you can, I think this link works. Just test the link. Yes, the link works. I'll go to that in a minute, but let me stay on the presentation for a second. Find the presentation. And so we'll talk about BGM in a minute, talk about that paper and get you to the essential part of that paper. The thing I wanted to convey, though, before we do that, is that you've now got the basics. So there are other models that are basically variations. I think of them as variations on Heath Jarrow Morton. They do different things. Some of the algebra is a little bit different, but most of it has the same sort of feel and format. And most of it is in the same sense that once you decompose what it's saying into little discrete steps, you can play with it in a way that makes it very much more intuitive than it is by trying to read the article. I don't know how much time any of you have spent trying to read academic articles, but but some of them they go straight to higher mathematics, and it becomes very difficult. And I have a well, so this is just sort of an aside personal story. When I was taking stochastic differential equations, I had a professor, and he was really just a superb professor. It was a year-long course. And it was very interesting. There were three main groups of people in the course. There were the math majors, there were the physics majors, and then there were the econ/finance majors. And the instructor, Tom Kurtz, was so good because he could give examples. First, he would go through the math proof. Then, after he was done with the mathematical proof, he would go through a physics example. And then after the physics example, he would go through an economics example or a finance example. So the funny thing was, he'd go through the math, and as he went through the math part of it, the mathematicians would sit there in their chairs nodding, "Oh yeah, now I get it." But the other 2/3 of the class would be sitting there like, what? And then he would go through a physics example, and the mathematicians and the finance people would be sitting there going, what? And then finally he would go through a finance example, and then the economists and finance people would be happy, but the mathematicians and the physics people would be sitting there going, what? But everyone got what they needed, but it was very hard. The aversion that I have to using stochastic differential equations is partly because as he did this, he would go very quickly. And he was one of those people who, I don't know if you've ever tried to like pat your head and rub your stomach at the same time. That's hard to do. But what Professor Kurtz used to do was he would write, he was right-handed, so he would write with his right hand on the board, and he would start from the left side of the classroom and move towards the right. And as he did that, he would have so this is how long ago it was. It was the era of chalk erasers. He would have an eraser in his hand, chalk and erasers. He would have an eraser in his hand, and as he was writing with his right hand, he'd be erasing with his left hand. So if you didn't take down the notes very quickly, you ended up spending half the night trying to fill in the parts that you missed because you didn't get them before he erased them. So that's left me always going back to basics rather than just working with the equations as they sit. It's an artifact of his course. Anyway, I digress. So we want to talk a little bit more about BGM versus HJM. And so BGM is Alan Brace, Darius Guterick, and Marek Musiela in Australia, who did that paper, as opposed to Heath, Jarrow, and Morton, who I think both Heath and Morton, Morton, two of them were at Cornell. So anyway, one's U.S., one's Australian. Doesn't really matter. Anyway, we don't really have time to go through the full BGM approach now, but there are a couple of takeaways of how they're different and how they're the same. So both BGM and HJM are in a no arbitrage framework. But with HJM, we're always looking at the price of pure discount bonds. and we start with the price from 0 to cap t, and we break that up from into an observable price from 0 to j, and then the forward from j to t. And so that breaking up makes it easy to do, and it lets us start from today and move forward. That's a little bit different than the way the market actually tends to be closer to working, and that's where there are rates used for swaps, and swaps have the feature that they accrue over a window, and then the rate resets and there's a new accrual window. And so really what you're dealing with much of the time is the effective rate for something that's going to accrue over the next window. So it's not like a zero coupon bond per se. And so part of what's done in BGM is to take, so they use L because it was written at the time when LIBOR was still around. Now everything's on overnight funding, secured overnight funding, but the notation stays, the LIBOR notation stays. There's some accrual window for LIBOR, and that accrual window is given by 1 over delta, and that is what's decomposed into zero coupon bonds. And so it's you have to first make an equivalence between the LIBOR accumulation, the accrual over the window, between the resets, and then you get the bonds. So there's basically there's an extra step to go through, and by going through that step, it changes it from what's called the spot measure, so moving forward from today, to what's called a forward measure, working from the LIBOR rates that would accrue over that time, and the accumulation that would accrue over the window of that LIBOR instrument staying, of that LIBOR rate staying in force. So that's like a real subtle difference, but it drives the different results, and you can see that. Yeah, I would suggest getting the BGM model. The BGM model I did just see on my computer, so I'm going to share that for a second. And what you see is the same the same format as the HCA model. Academics, and I suppose I'm sort of one, prefer to work in the compactness of continuous time, but in practice that may not be the most intuitive thing. But what we end up with is something that should look. So here's the LIBOR accumulation and getting the discount bond. Oops. But what they're doing is getting back to a log normal volatility structure. So we use what's called log normal. The little f's are normal, but e to the f isn't normal. And so you end up with something that's very similar, but with some difference depending on the LIBOR accumulation rate. And so that changes the call it the accumulating function. But it's a very similar idea. Screen share. It goes back to a screen share. I'm sorry, it goes back to an accumulation function, just moving in a different direction. So we're not really running out of time, but before we talk about implementation and answer questions, what you want to do is you need to find, so whenever you're doing a trade, you're given some of the terms of the trade, like the tenor of the trade, if there's a strike on the trade, the expiration of the trade. That's usually, that's important stuff. You need that to price a trade, but that stuff usually comes from the client. Client wants to cover a certain time window. The client's looking for particular strikes. They may have some, oftentimes when in trading, the client comes in and wants to reduce risk in some area or eliminate the risk of something or take risk in something. And they're pretty vague about how they want to do it. And then they want, you give them a solution and they'll say, that's great. That's a great solution, but is there a cheaper way to do it? And so you end up with a lot of the structures, especially the exotic structures, as being ways of making the trade cheaper. Either cheaper in terms of less money up front, less overall risk. Generally, it's less money or no money up front. And so you put in features that cheapen make it cheaper for the client to do the trade. I mean, it's like anything else. Customer walks into your store and asks, if you're selling suits and you've got, there's $5,000 suits, and the customer says, well, you get any cheaper suits? Same in derivatives trading. Everyone wants to find the lower cost. So the terms often change, but the things you need that you have to find as the seller are the forwards and the volatilities that let you do the pricing, that really drive the pricing. So you're the one that owns those models. And so you spend a lot of time trying to find the right forward that gives the right price, that you can then use to quote to the client in a way that lets you obtain some P&L for doing the trade, some profit for doing the trade. And so what these HJM models do is, if you go back to anywhere where we were, just any one of these, you get an idea for the forward and you get an idea for the volatility. And so those become inputs into your model, and that allows you to price the trade. And so whether it's HJM or BGM or any variation, there are others, like there's another fixed income model that's popular, and that's Black Karazinski. So let me take a whiteboard for a second. Let me just take a whiteboard for a second and just draw a distinction between what we've been doing is that these little f's are normally distributed. And I apologize for my stylus writing. So these little f's are normally distributed. And so when we calculate e to the minus f, the expectation we have something with an analytic answer that if we take logs, we can take logs of we take the log of that expectation. Word. Handwriting is terrible. If we take the log of that, we get this. I'll call this F hat. Call it F hat, just to delineate that it's kind of different. And so this is linear. This is a very simple expression. It just says that the expectation, the log of the expectation, is two numbers added together. There's the Black-Karaszewski model, which says that the log of F is normally distributed. And that's a very popular model for pricing caplets and things like that. But this model isn't no arbitrage. So not all models that are used on Wall Street rule out arbitrage. There are some models that are used for pricing instruments that don't rule out arbitrage, but they're still used because even though you have to recalibrate them and you know the pitfalls of them, if you understand the pitfalls of the model that you're using, you can use it even if you know it's not a great model, because you know how it's gonna go wrong. And so we didn't cover all the variations, but just as we covered HJM, what you learn, and so I guess I should call this mu star sigma squared star because they represent different units from the other one. Just as we went through HJM, what you were learning to do, it may not seem like it, but what you were learning to do was to find the forward that would be useful in say a black model of a caplet, and or Black-Scholes model, basically Black-Scholes but applied to interest rate caplets, where you're putting in the forward. So you learn to find that mean. We didn't talk about calibration, but that would be the next step to before implementation. And so stop that share. Back to this final page. And so we've gone through how to do that. And so you know how to do that with HJM. There are other models that do similar things like BGM. There are some subclasses of HJM like Holy and Vasicek very popularly used. What's interesting is both Holy and Vasicek, although they fit in the no arbitrage class, and they fit as special cases of HJM, those models are older than HJM. They were derived first, and it was really an HJM. When HJM came out, it was not only an innovation to understand how no arbitrage models would be important, but it was kind of a curious quirk that some models like Vasicek and Holy turned out to be already in the class of no arbitrage models, and other models like Cox Ingersoll Ross or Black Karasinski turned out to be not in the set of no arbitrage models. And then there were extensions. So there's BGM is one extension that's occurred since HJM. There's another extension that directly tries to take the information from caplets and floors that are observed. You observe those prices in the market, so then integrate that information into your forward curve building, knowing that no arbitrage conditions have to hold, and you can back into to me it's a very to me both BGM and this other volatility methodology they're all subsets of BGM of HJM, where they all belong in the same class because they're all in the no arbitrage class, and that gives rise to some of the best modeling and pricing that you see being done on Wall Street, and some of the useful stuff for pricing and for risk purposes as well, because you don't whenever you're trading, you don't simply price an instrument and then be done with it. The price of an instrument is really derived from how much it's going to cost to hedge the instrument. And so for good pricing models, a good pricing model is built up from the cost of hedging. And that's the question that every risk manager asks every trader when there's a new trade is, how are you going to hedge it? Which is really the same as asking, how did you price it? If you know how it was hedged, you know how it's going to be hedged, you know how it's being priced. The price is basically the cost of the hedge plus a markup. And that's sort of the fundamental rule of derivatives pricing. Any questions? It doesn't look like there are any questions. And again, the screen I'm looking at has names, but I see no faces. So I don't know if people have walked away or are still around. Anyway, if there are no other questions, I can give you about 10 minutes of your day back. And I appreciate you spending time with me today, because I think this is really interesting stuff, and it's really a lot. So let me drag on for one more second. It's really fun. So equity is fun, currency is fun, commodities are fun, credit is fun, because you're thinking about, well, what's the distribution of the, say the equity at some terminal date, and how do I find that distribution of equity price of that equity's price on the terminal date and build rules around it so I can price a derivative, and maybe there are some steps intermediate to that where I can exercise early, that sort of thing. So you can have fun with that. But that's nowhere near the level of fun that you get with rates, because with rates, you're taking a whole curve and you're moving that curve out in time. And as you go through time, you have to take that whole curve along, and the curve has to remain self-consistent. So, in equity, you don't have to worry about the relationship between IBM and Apple. Who cares what their relationship is? But you do have to care when you're talking about rates, when you've got the 1-year rate and the 2-year rate on the same curve. And that does matter. And so it's a fascinating world, because it's just that much more complex and involved. So I heartily recommend it. Oh, plus on rates, if you're in rates, if you're in the rates world, instruments go out 60 years regularly. You find most of the action is in the 30-year, in the first 30-year window, but you can get swaps that go out 60 years. There are some century bonds that go out 100, but almost all the action is in 60 years. If you're dealing with currencies or equity, you're only going out a couple of years. So you really have to, when you've got a short window, a small error in a model doesn't have all that much time to accumulate. But when you're going out 60 years in a model and you're stepping out quarterly, there are a lot of steps that you're going to undertake where, if you're wrong, those mistakes can accumulate, and it can be a disaster or an opportunity, depending on which side of the trade you're on. So I recommend it. I recommend rates, things just as a fascinating world. Questions? All right, so I guess I'll give you 15 minutes of your life back early. And I thank you. I appreciate you spending time with me today. I hope it was worthwhile for you. Thank you.